Hello, everyone. Welcome to today's session. I'm excited to introduce our topic, Unit 1 Periodic Properties. This is Batch 2. On this first slide, we're kicking off with an overview of what's to come. We'll explore the fundamental periodic properties of elements, understand how they vary across the periodic table, and see how this knowledge helps us in chemistry. So let's get started and make this a productive and engaging session. Let's start by introducing our team members who contributed to this project. First, we have Srivatsan, with the ID RA 2511003020502. Next is Amrutha Varshni T, identified as RA 2511003020503. Shyam is also a key member, with the ID RA 2511003020504. Then there's P. Meghavarshni, whose ID is RA 2511003020505. Sandeep M. joins us with RA 2511003020506. We also have Kuruthik Pranav JS, identified as RA 2511003020507, and Pranav Kumar Kartik, with ID RA 2511003020508. Jashwanth is part of the team as well, holding the ID RA 2511003020509. Rithik ID is RA 2511003020510, and Deepa's is RA 2511003020511. Finally, we have Sanjana, with the ID RA 2511003020512. Highlighting these names and IDs underscores the diverse and collaborative effort behind our project. Each member has played a vital role, contributing their unique skills to achieve our overall goals. Recognizing the team like this not only shows the strength in collaboration, but also reminds us that successful projects are built on collective effort. Let's take a closer look at the table of contents for today's presentation. We'll start with an introduction to coordination compounds, which are fascinating because they involve a central metal atom bonded to surrounding ligands. Moving on, we'll cover the basic principles that govern these compounds, helping us understand their structure and behavior. Then, we'll explore crystal field splitting, a key concept that explains how the energy levels of d orbitals are affected in these environments. We'll also look into the factors that influence crystal field theory, such as the nature of ligands and the metal's oxidation state. Next, we'll dive into the HSAB theory, which helps us predict how acids and bases interact in coordination chemistry. Finally, we'll discuss some of the practical applications of these compounds, along with their limitations, to see how they're relevant in real-world contexts. This roadmap will guide us through the core concepts and connect everything back to the overall theme of understanding coordination chemistry. Let's delve into the world of coordination compounds. These are special types of compounds where a central metal ion is bonded to molecules or ions called ligands. Think of the metal as the core and the ligands as its surrounding partners forming a complex structure. For example, take the compound Cu, NH3-4SO4. Here, a copper ion is surrounded by 4 ammonia molecules acting as ligands. This brings us to Werner's coordination theory, which was a groundbreaking development in understanding these compounds. Werner introduced the idea of coordination numbers, essentially how many ligands are attached to the central metal, and the geometries these complexes adopt, like octahedral or tetrahedral shapes. And to help you visualize this, imagine the coordination complex image I've inserted here. It really helps to see how the ligands are arranged around the metal. Overall, understanding these key concepts is essential because it sets the foundation for exploring their properties and applications further along in our presentation. Let's now look at the basic principles of crystal field theory. A complex is essentially a central metal ion surrounded by various ligands. Think of it as the metal at the center with these molecules or ions attached around it. In CFT, the bond between the metal and the ligands is considered purely ionic, meaning it's mainly electrostatic attraction rather than covalent sharing of electrons. Ligands themselves can be negative, neutral, or sometimes true donors, depending on their nature. An important point is that the interaction between the metal and ligands is primarily repulsive. These repulsive forces are what cause the 5 degenerate d orbitals of the metal ion to split into 2 different energy sets, known as T2G and N. This energy difference is called the splitting energy, and it's fundamental to understanding the electronic structure and properties of these complexes. It's also crucial to emphasize that, according to CFT, electrons don't actually enter or occupy the metal orbitals in the way we might think of covalent bonding. There's no sharing or mixing of orbitals. Rather, the effect is purely due to electrostatic interactions. Because of this, the overlapping of orbitals isn't involved in the splitting process. Now, the number and spatial arrangement of ligands around the metal ion, whether they form octahedral, tetrahedral, or other geometries, directly influence the crystal field. Different arrangements produce different electrostatic environments. And because the crystal field varies with these arrangements, the relative energies of the 5D orbitals also change accordingly. This variation impacts many properties, such as absorption spectra and magnetic behavior, which are key to understanding the chemistry of these complexes. Let's take a closer look at the d orbital shapes and their energy levels. There are 5 degenerate d orbitals, which means they all have the same energy in a free atom. These orbitals are named dxy, dis, dxz, dx to minus y2, and dz2. Each of these has a unique shape and orientation in space, which plays a crucial role in how they interact with ligands. Now, when we introduce ligands around the metal ion, something interesting happens. The degeneracy is broken, and the energy levels split, a phenomenon known as ligand field splitting. This splitting depends on the type of ligand and how it interacts with each of the d orbitals. Understanding this splitting is essential because it influences properties like color, magnetism, and reactivity of coordination complexes. So, recognizing how these 5D orbitals behave and split under ligand influence helps us grasp the broader concepts of coordination chemistry and electronic structure. Let's start by looking at the concept of crystal field splitting. To really understand how transition metal complexes behave, we need to grasp the spatial arrangement of the d orbitals. In a free gaseous metal ion, these 5d orbitals are degenerate, meaning they all have the same energy. Now, when a symmetric field created by ligands surrounds the metal ion, things change a bit. If this ligand field is spherically symmetric and negatively charged, the d orbitals will still remain degenerate, but their energies will shift compared to the free ion. This shift is fundamental to understanding how the complex interacts with light, how electrons are arranged, and the overall stability of the complex. So, recognizing how the spatial orientation of these orbitals influences their energy levels is key to mastering crystal field theory, and by extension, the behavior of transition metal complexes. Now, let's talk about octahedral crystal field splitting. When a metal atom or ion is surrounded by 6 ligands arranged octahedrally, we see a specific kind of electron repulsion at play. These repulsions happen between the electrons in the d orbitals of the metal and the electrons in the ligands. What's interesting is that this repulsion isn't the same for all the d orbitals. The orbitals that point directly towards the ligands, namely dx2y2 and dz2, experience stronger repulsion because they are aligned along the axes where the ligands are located. As a result, these orbitals have higher energy compared to the average energy level in a spherical crystal field. On the other hand, the dxy, dis, and dxz orbitals are oriented between the axes, meaning they don't point directly at the ligands. This means they experience less repulsion and thus have lower energy than the average in the spherical field. Because of these differences, the energy levels split into 2 distinct groups. The first group, called T2G, includes the dxy, dis, and dxz orbitals, which are lower in energy. The second group, called, for example, includes the dx2y2 and dz2 orbitals, which are higher in energy. Understanding this splitting is key to grasping the behavior of transition metal complexes, especially how they absorb light and exhibit various magnetic properties. It's a fundamental concept that links the structure of these compounds to their electronic and chemical behavior. Now, let's talk about what happens to the degenerate energy levels when a ligand is present. This process is called crystal field splitting. Essentially, the degenerate orbitals split into different energy levels due to the electrostatic interactions with the ligand. The key point here is the difference in energy between the T2G and 4-example levels, which we denote as delta O. The subscript O stands for octahedral, indicating the geometry we're considering. This energy difference is crucial because it influences the electronic structure and properties of the complex. Another important aspect is that not all ligands produce the same effect. Some ligands generate strong fields, leading to a large crystal field splitting. Others produce weaker fields, resulting in smaller splitting. This variation impacts various properties, like color, magnetic behavior, and reactivity of the complex. Overall, understanding crystal field splitting helps us grasp how different ligands influence the electronic environment of the metal's center, which ties into the broader theme of how ligand interactions determine the properties of coordination compounds. Let's now look at the tetrahedral crystal field splitting. When a metal ion is in a tetrahedral environment, the five-fold degenerate d orbitals split into two distinct energy levels. This splitting can be represented by two sets of orbitals, which we denote as T, D. Now, an important point here is how the electrons in these orbitals are affected by the ligands. Electrons in the dx2y2 and dz2 orbitals experience less repulsion from the ligands compared to those in the dxy, dis, and dxz orbitals. As a consequence, the energy of the dxy, dis, and dxz orbitals gets raised, while the energy of the dx2y2 and dz2 orbitals is lowered. Another key point is that in tetrahedral complexes, there are only 4 ligands, unlike octahedral complexes which have 6. This means the overall ligand field strength is weaker because fewer ligands are involved, and thus, the total negative charge exerted by the ligands is less. Lastly, it's interesting to note that the direction in which these orbitals point does not directly align with the approach of the ligands toward the metal ion. This non-coincidence influences the overall splitting pattern and the electronic properties of the complex. Connecting this to our broader theme, understanding how these orbitals split in different geometries helps us grasp the electronic transitions, magnetic properties, and reactivity of these complexes. So, in a tetrahedral coordination compound, the repulsions between the ligands and the d orbitals lead to the formation of two distinct energy levels. The first set, called T2, includes the dxy, dis, and dxz orbitals, and these end up at a higher energy level. The second set, called E, consists of the dx2y2 and dz2 orbitals, which are actually lower in energy. Now, an important point to remember is that the crystal field splitting in a tetrahedral complex is intrinsically smaller compared to an octahedral field. This is because there are only about 2/3 as many ligands, and these ligands have a less direct effect on the d orbitals. This difference in ligand number and position means that the stabilization of the E set is represented by a value of -6 dq, while the destabilization of the T2 set is represented by +4 dq. Understanding these energy differences helps us see how the geometry influences the electronic structure and stability of these complexes, which ties back into the overall theme of how ligand arrangements affect their properties. Let's take a closer look at the crystal field stabilization energy table. This table is crucial because it helps us understand how the energy levels of d orbitals change when ligands approach a transition metal ion. Essentially, it shows how different electron configurations influence the stability of a complex. The key points to note here are the values assigned to various configurations, which tell us how much stabilization or destabilization occurs. This stabilization energy is a vital factor in predicting the overall stability of a complex and its color, reactivity, and other properties. By analyzing this table, we can better grasp why certain geometries and electron arrangements are favored in coordination chemistry. It ties directly into our broader theme of understanding how electronic structure influences chemical behavior. Let's explore the factors that influence crystal field splitting. First, the nature of the ligands plays a crucial role. Strong field ligands, such as cyanide or carbon monoxide, tend to produce a high splitting energy, meaning they cause a larger gap between the d orbitals. Conversely, weak field ligands like iodide or bromide generate a lower splitting energy, resulting in a smaller gap. Next, the oxidation state of the metal ion also affects splitting. Typically, higher oxidation states lead to increased splitting energy because the metal ion's positive charge pulls the ligands closer, strengthening the crystal field effect. Now, regarding geometry, splitting is generally more pronounced in octahedral complexes compared to tetrahedral ones. This is because the arrangement of ligands around the metal center influences how the d orbitals interact with the ligand's electron clouds. Finally, when we look at electronic configuration, we have the concept of high-spin versus low-spin complexes. Depending on the ligand strength and the splitting energy, electrons will either pair up or remain unpaired, which significantly impacts the magnetic and spectral properties of the complex. All these factors together help us understand the behavior and properties of different coordination compounds in crystal field theory. Let's take a closer look at some key atomic properties. First, atomic radii. This is basically the distance from the center of the nucleus to the outermost electron shell. It helps us understand the size of an atom. Next up is ionization energy. This is the amount of energy needed to remove the most loosely bound electron from a gaseous atom. It's a great measure of how easily an atom can lose electrons and turn into a positive ion, or cation. Then we have electronegativity. This tells us how strongly an atom in a chemical bond attracts the shared electrons. It's crucial for understanding how atoms interact in molecules and how bonds form. Finally, electron affinity refers to the energy released when a neutral gaseous atom gains an extra electron. This process creates a negative ion, and the amount of energy released gives us insight into how eager an atom is to accept electrons. All these properties are interconnected and help us understand the behavior of elements, especially when considering their role in chemical reactions and bonding. Let's take a closer look at the spectrochemical series. This is essentially a list that arranges ligands based on their ability to split the d orbitals of a central metal ion in a coordination complex. Now, this splitting is known as the crystal field splitting energy. This energy difference plays a crucial role because it influences the electronic structure of the complex, as well as its color and magnetic properties. Ligands are ranked from weak field to strong field. The key idea here is that strong field ligands cause a larger splitting of the d orbitals, which can significantly affect how the electrons are distributed. This, in turn, impacts the overall characteristics of the complex. Understanding this series helps us predict and explain the behavior of different coordination compounds, especially when it comes to their electronic and optical properties. It's a fundamental concept that ties together the ligand strength with the observable properties of the complex, making it an essential part of our overall understanding of coordination chemistry. Let's start by exploring the basic idea behind HSAB theory. The classification of Lewis acids and bases as either hard or soft helps us understand their interactions better. Now, it's important to remember that acids and bases aren't strictly one or the other. Many fall somewhere in between, which we call intermediate. This classification depends on three main factors. First, charge density, which is essentially the charge-to-size ratio. The higher this ratio, the more likely it is to be a hard acid or base. Second, polarizability, the ease with which the electron cloud can be distorted. And third, whether the interaction is more covalent or ionic in nature. Focusing on hard acids and bases, these tend to have a high charge density, meaning they carry a significant charge relative to their size. They're also not very polarizable, so their electron clouds are relatively rigid. The bonding interactions they form are primarily ionic, Think of it as a strong electrostatic attraction. In general, hard acids are often metal ions with high positive charges and small sizes. For example, early transition metals in the 3D series tend to be hard Lewis acids because of these characteristics. When it comes to hard bases, we're typically talking about small anions or neutral molecules, particularly those with heteroatoms from the second row of the periodic table, like nitrogen, oxygen, and fluorine. Some typical examples of hard acids include H+ ions, O2 ions, hydroxide O, fluoride F, and metal ions like Fe3+ and Al3+. Notably, oxygen atoms are always considered hard, and nitrogen atoms usually fall into this category as well. So, understanding these distinctions helps us predict how different acids and bases will interact, which is a key part of mastering HSAB theory and applying it effectively in chemistry. Now, let's talk about soft acids and bases. In general, soft acids or bases are characterized by having a low charge density, which means their positive or negative charge is spread out over a larger volume. This makes them more polarizable, so their electron clouds can easily distort in response to interactions. Because of this, they tend to form bonds that are more covalent rather than ionic in nature. Usually, these atoms or ions have a low overall charge and often a larger radius, which contributes to their softness. When it comes to typical soft acids, we're often looking at transition metals that have a +1 charge, like copper in its +1 oxidation state, Cu+. You'll also find metals in the late 4D and 5D series, such as cadmium, Cd2+, and mercury, Hg2+, which are also classified as soft acids. These elements are usually in the second or third row of the periodic table and tend to have filled or nearly filled d orbitals, which influences their ability to form covalent bonds. On the other side, soft bases tend to be larger anions or neutral molecules. For example, iodide, I, and sulfide, S2, are classic examples of soft bases. Their larger size and polarizability make them more willing to share their electrons with soft acids, facilitating covalent bonding. Understanding these concepts is crucial because the interaction between soft acids and soft bases often dominates in many coordination and organometallic chemistry scenarios. Recognizing which species are soft helps us predict the stability and nature of the complexes they form. Let's talk about isomerism. Isomerism occurs when two or more compounds share the same molecular formula but differ in how their atoms or groups are arranged. This means that even though they have the same number and type of atoms, their structures are different, which can lead to different properties. When we look at coordination compounds, isomers differ specifically in the structure or the spatial arrangement of ligands around the central metal ion. This is a key concept because it influences how these compounds behave and interact. There are mainly two types of isomerism to keep in mind: structural isomerism and geometrical isomerism. Structural isomers have different connectivity between atoms, meaning the bonds are arranged differently. Geometrical isomers, on the other hand, differ in the spatial arrangement of ligands, especially around a double bond or a metal center, which can affect their physical and chemical properties. Understanding these differences is essential because it ties back to our overall theme of how molecular structure influences properties and reactivity in coordination chemistry. Recognizing these types of isomerism helps us predict and explain the behavior of different compounds. Let's dive into some types of structural isomerism. First, we have ionization isomerism. This occurs when compounds, despite having the same overall composition, produce different ions when dissolved in solution. So even though their formulas are identical, their behavior in solution can vary quite a bit. Next, we look at hydrate or solvate isomerism. Here, the key difference lies in the number of water molecules associated with the compound. These water molecules can be either inside the coordination sphere or outside, and this variation leads to different isomers. Finally, we have linkage isomerism. This happens with ambidentate ligands, which are capable of attaching through different donor atoms. When a ligand can connect through more than one atom, it can form linkage isomers by attaching in different ways. These types of isomerism are crucial because they influence the properties and reactivity of coordination compounds, tying back to the overall theme of how structure impacts function. Now, let's move on to structural isomerism, specifically focusing on coordination isomerism. This type of isomerism occurs in compounds that contain both cationic and anionic complexes. The key idea here is that ligands can actually exchange between these cationic and anionic parts, leading to different arrangements even though the overall chemical formula stays the same. Essentially, it's about how the ligands are distributed within the complex, which can significantly affect the compound's properties. Next, we have coordination position isomerism. This is particularly relevant in polynuclear complexes, where multiple metal centers are involved. Here, the ligands occupy different coordination sites around the metal centers. So even if the ligands are the same, their positions in the structure change, leading to different isomers. Both these types of isomerism highlight how flexible and diverse coordination compounds can be. They remind us that the arrangement of ligands, where they are and how they are shared, can create entirely different structures with potentially different reactivity and properties. This is a crucial aspect in understanding the behavior of complex compounds in chemistry. Let's talk about geometrical isomerism. This type of isomerism occurs because of different spatial arrangements of ligands around the central metal ion. Essentially, even though the same ligands are attached, their positions in space differ, leading to distinct compounds. It's most common in complexes with square planar and octahedral geometries. Focusing on square planar complexes, which often have the formula Ma2B2, we see two main types of isomers, cis and trans. In the cis isomer, the identical ligands are next to each other, meaning they're adjacent. Conversely, in the trans isomer, the identical ligands are opposite each other, across the central ion. For example, if we consider NH3 as the ligand, in the cis arrangement, both NH3 groups are next to each other. In the trans arrangement, they are positioned opposite each other. Recognizing these differences is key because they can influence the chemical properties and reactivity of the complexes. So, understanding geometrical isomerism helps us see how the spatial arrangement affects the behavior of coordination compounds, linking back to the overall theme of how structure influences properties in coordination chemistry. Now, let's look at geometrical isomerism in octahedral complexes, specifically those of the types Ma4B2 or Ma3B3. These complexes can exhibit interesting forms of isomerism due to the different arrangements of ligands around the central metal atom. One key concept here is cis and trans isomerism. In cis isomers, similar ligands are adjacent to each other, meaning they are on the same side of the complex. Conversely, in trans isomers, the identical ligands are opposite each other, positioned across the center of the complex. Recognizing this difference is crucial because it influences the properties and reactivity of the complex. Another important type is FAC and MER isomerism, which applies specifically to Ma3B3 type complexes. The FAC, or facial, isomer has three identical ligands positioned on the same face of the octahedron, creating a triangular face with those ligands. On the other hand, the MER, or meridional, isomer features the three identical ligands aligned along a meridian plane, forming a straight line through the complex. Understanding these arrangements helps us see how different spatial configurations can lead to distinct isomers, even though they contain the same ligands. This not only showcases the diversity of geometrical isomerism, but also highlights its importance in determining the properties of coordination compounds. Thank you so much for your time and attention today. I really appreciate the opportunity to share these insights with you. Remember, the key points we've discussed highlight the importance of understanding the core concepts and their practical applications. I encourage you to take these ideas forward and think about how they can be integrated into your own work or projects. Ultimately, Our goal is to make a meaningful impact by applying what we've learned. Thank you again for being such an engaged audience.